Greetings and welcome to this presentation on potable water systems. This is one in a series of presentations for the operators and managers of water and wastewater utilities for Native American tribes and Alaskan Native villages. In this presentation we're going to cover a number of topics related to public water supplies. We'll start with the definition of what actually is a public water supply. We'll look at the components of a surface water system that takes water from a river or a stream or a reservoir and runs it through a treatment facility before it's sent out to its customers. We'll also look at the components of a groundwater system, where water is withdrawn from a well and used for drinking water purposes. We'll talk for a bit about source water protection and how we can manage land use within the area around our drinking water supply in order to protect the water and keep it from getting contaminated prior to it coming into the system. We'll also talk a little bit about the chemicals and contaminants that impact our drinking water systems, as this will be helpful for the presentations that follow on the distribution systems for drinking water supplies and water storage tanks that are connected to these distribution systems. We'll look at chemicals that are naturally occurring in the environment, as well as those chemicals that we may deliberately or inadvertently discharge into the environment, into surface waters, or into groundwater systems. So let's begin by looking at the definition of a public water supply. This definition is designated or defined by the Safe Drinking Water Act, and it states that a public water supply is one that provides piped water for human consumption to either 15 or more service connections or an average of 25 people each day for a minimum of 60 days each year. A service connection is a line from the distribution system into a home, business, or an apartment complex. You need to have 15 of those to be considered a public water supply, or in the alternative, you have to serve 25 people with your public water supply system, and you need to provide them water on a daily basis for at least 60 days each year. An example of a 25-person public water supply could be an apartment complex, where more than 25 people live within the building, but there's only one service connection coming into the system from a well or a drinking water supply outside the building. Public water supplies can be divided into two types: community water systems and non-community water systems, and we'll talk about those definitions now for a few moments. A community water system is one that serves either 15 or more service connections or 25 residents, but those residents or people on those service connections are the same people every day. Examples of these could be a mobile home park, a subdivision, a city or a town, or most municipal water systems. A system serving a tribal community, where the people are living there on a day-to-day basis, would most likely be considered a community water system. And our concern for these systems are both the acute impacts of contaminants that may be within the drinking water that could harm people in the short term, as well as the long-term chronic health impacts from anything that may be in the drinking water supply. If people are drinking the water on a day-to-day basis, you have to look at both acute and chronic health effects. Now, the alternative is a non-community water system. And again, there's two different types of non-community water system: a non-transient non-community water system, as well as a transient non-community water system. We'll start by talking about the non-transient non-community water system. That sounds like a lot, but the definition is actually fairly straightforward. A non-transient system is one that serves the same non-resident population each day for more than 6 months out of a year. A great example of this is a school, where children and teachers and staff are at the school every day for at least 6 months out of the year, and they're drinking that water supply every day that they're within the school. A business could be another type of non-transient, non-community water system. And again, as people are drinking the water on a day-to-day basis, the concerns are going to be both for acute and chronic health effects. In contrast, there's also a transient non-community water system, which is serving a different non-resident population at the same location on a daily basis for at least 6 months in a row. A great example of this could be a restaurant, which may not be serving the same people every day, but is open for more than 6 months a year. A campground would be another example of what a transient non-community water system would be. The primary concern will be what are the acute health effects from any contaminants that may be within the drinking water supply. Knowing these definitions of a public water supply, we now turn our attention to where the water comes from that feeds these systems. We're going to start with a brief overview of the hydrogeology or the science of drinking water systems so we can understand better where our water comes from and understand where contaminants may enter our drinking water systems. We'll then provide an overview of the components of a surface water system and the treatment steps that take place to take water from a stream or a reservoir and convert it into potable water. And following that, we'll also look at an overview of a groundwater system and show you the components of the well and the systems that go into that, and do a brief overview of some of the operation and maintenance tasks that are needed to manage both a groundwater and a surface water system. Looking at the science of drinking water, we start by understanding where our water comes from and how it moves through the environment. And we can do this on a very basic level by looking at the hydrologic cycle, as shown on this figure here. We'll start by looking at water that's out in the ocean that's evaporating into a gaseous state and creating the clouds up in the atmosphere. The water moisture in the atmosphere continues to grow until it hits a point where it turns into rain, where it falls back down on the land surface. A portion of this water is going to flow overland along the ground surface into a river or a stream. It may be collected within a reservoir and provides the source of water for surface water systems. As we look at surface water systems, our main concern will be contaminants that enter the water through surface water runoff. So sediments that erode off the ground surface, contaminants that may be in stormwater that hits parking lots and roads, such as road salts, bacteria, metals, or hydrocarbons, can enter the stream or the reservoir through surface water runoff and affect the quality of the water that we drink. A portion of the water that falls from precipitation also soaks down into the ground and creates what is known as recharge that fills the underlying groundwater system that can serve as a source of water for drinking water wells. This groundwater doesn't stay static, it moves, so the recharge enters the aquifer from the top. Groundwater flows in a down gradient or downhill direction where it eventually discharges back to a surface water. So there can be a component of surface water that's coming from groundwater. As the surface waters collect and move downstream, they eventually return to the ocean, and we start the hydrologic cycle all over again. On this next slide, we can look more closely at both the surface water flow entering a surface water body and the recharge to groundwater and how groundwater moves below the land surface. We have rainfall falling on the ground surface. A portion of that rain is going to move as overland flow, as shown by item 1 on the slide, and move down towards the surface water. The volume of water that moves as overland flow will depend on the permeability or the tightness of the rock or soil along the land surface, as well as the topography or the slope of the land surface. If rain is falling on a steep slope, it's more likely to turn into overland flow or stormwater runoff as opposed to soak into the ground. If the rain is falling on a flatter, more sandy or more permeable area, the water is more likely to infiltrate down into the ground and enter the underlying aquifer system. As this slide shows, under number 2, groundwater flow, the rain is soaking into the ground as groundwater recharge. It enters the aquifer system and it's moving across the slide and eventually discharging back out to the surface water body. In some areas, there can be some tight or confining layers just below the land surface that can create shallow subsurface storm flow or interflow that can be especially seen in areas of steep slopes where there can be some runoff that's moving just below the ground surface but moving downhill without a lot of it infiltrating down into the ground or into the aquifer system. Our next focus is to look at drinking water systems that take their water from surface water intakes or from streams and rivers or lakes and reservoirs. There's a variety of different types of intakes where these systems collect their water. They can be at the surface, at the edge of a stream or a river, or at a dam created that's used to develop a reservoir. Water can be taken from the surface of the system. It can also be taken from a depth below the water surface, and sometimes water systems will have an intake both along the surface, at the edge of a river or stream, or at the top of a dam, as well as further down in the water column. The surface water treatment process includes 7 steps. The first is the water intake, which we've covered on the previous slide. Water that's coming in through the intake then runs through a screen to minimize the debris that may be within the system. There's a series of steps then to remove the particles and the chemicals that may be in the water, which we'll cover with coagulation and flocculation, as well as sedimentation and filtration. Once the water is treated, it is disinfected, and at that point, if necessary, corrosion control chemicals are added to neutralize the pH or minimize the acid within the water. This next slide shows in a graphic form these different steps of the surface water treatment process, with the water coming from the intake, the sediments and particles being removed through the coagulation and flocculation process, as well as the sedimentation and filtration processes, followed by disinfection, and then the water is sent out into the distribution system. Let's look in a little more detail at these processes, starting with the coarse screening at the beginning of the treatment train. This is used to remove the aquatic plants, the sticks, the leaves, and other floating debris that may come into the system through the intake. Following this coarse screening, the next step is to remove the finer particles or the suspended solids that are present in the surface waters. The goal is to take these suspended solids and make them settle out of the water, and we start that in a 2-step process known as coagulation and flocculation. Many of the suspended solids that are in the water during the treatment process have a negative charge and tend to repel each other. And the goal of the coagulation process is to add a chemical that allows these particles to attach to each other, eventually creating larger particles or clumps that are heavy enough that they will settle out to the bottom of a treatment tank. This settling or clumping process is known as flocculation. There's a variety of different types of chemicals that can be used as coagulants to allow the suspended particles within the water column to stick together. Often inorganic coagulants such as aluminum or iron salts are used, and in some situations organic chemicals are used. The aluminum and iron salts have the potential to adjust the pH of the water after the coagulation and flocculation has taken place, so that's a consideration in their selection. Organic chemicals don't impact the pH, but they can be expensive to use, and there are other considerations with their application as well. So as you select a coagulant to use with your drinking water system, one of the considerations you'll have to look at is how the pH of the water may change and how that may affect future treatment processes prior to the water going out into the distribution system. Once the coagulant is added, there's a gentle mixing process to allow the particles to flock together, the flocculation process. This typically lasts from 10 to 20 minutes or up to an hour, depending on the design of the system. And the goal here is to gently mix the coagulant chemical in the water column and allow it to do its work, bringing the particles together so they are large enough to sink to the bottom of the treatment tank. Once the flocculation process has been finalized, there's a sedimentation step within the treatment process. The water is no longer mixed, but is allowed to slow down and settle. This process allows gravity to work and remove the flocculated particles, which are collected as a sludge at the bottom of the tank. This process typically lasts 1 to 4 hours, and you want to ensure that the water movement through the sedimentation tank is slow enough that it doesn't disrupt the sludge layer that is being collected on the bottom. Otherwise, the whole coagulation, flocculation, and sedimentation process gets disrupted. The final step in a typical surface water treatment process is filtration. The filtration process is one last protective step to remove the finer particles that may not have settled out during the preceding processes. The effectiveness of this filtration process is judged by measuring the turbidity of the water, or the level of suspended solids that remain after the water has passed through the filter. Testing is typically done on a 15-minute basis to ensure the effectiveness of the filter and make adjustments as necessary to ensure clean water is sent out to the distribution system. There are a variety of different types of filtration processes that are used, and the selection of which filtration process to use will depend on the quality of the water that is coming into your system and whether or not you have arsenic or uranium or other unique chemicals that may require special filtration in order to remove them. We're going to talk about 3 of these filtration processes, including the gravity rapid sand filtration process, the different types of membrane filtration with a focus on reverse osmosis, and then cartridge filters, which can be successful for smaller surface water treatment systems. The gravity or rapid sand filtration beds are the most common type of filtration system for drinking water supplies. They consist of layers of sand atop or below an anthracite coal layer, and the water is discharged to the top of the filter, and it flows by gravity down through these layers, removing the finer particles that still may remain within the water column. The particles or suspended solids that are in the water are trapped in the pore spaces of the filter, and the clean water exits the filter out the bottom. Once too many suspended particles have been trapped within the filter, it needs to be cleaned, and this is done through a backwash process where water is discharged upwards through the filter, dislodging the particles that may have been trapped within the pore spaces. Those are collected and removed from the water column so they're no longer present within the filter. Membrane filtration provides a way of removing some of the more difficult chemicals to treat, such as arsenic or higher levels of suspended solids or perhaps uranium. One of the more common types of membrane filtration is reverse osmosis, which can provide a good way of removing many of these more exotic chemicals. A filter with a membrane with very small pore sizes is used to do the filtration process, and water pressure is the driving force, forcing water through the filter. And typically these filters are sized such that only the water molecules themselves can move through the filter, and most of the contaminants are trapped on the other side of the filter. This can create very clean drinking water. For smaller drinking water systems, and even private wells or smaller public water supply wells, cartridge filters do a very good job of removing microbes and reducing turbidity within the drinking water system. These are typically small cartridges that are placed within a canister that's connected to the water supply line, and the pressure of the water moving through the system moves the water through the filter. These filters need to be removed and exchanged on a regular basis, and the size of the pore spaces that the filter has will depend on the type of material that you're needing to remove. If it's removing larger suspended particles, the pore size can be bigger. If it's removing smaller suspended solids, it will need to be a smaller pore size filter. And often if there's a variety of different size of sediments or particles that need to be removed, the filters are used in series, with the larger filter size first, followed by the smaller one, in order to remove the larger particles and prevent them from clogging the smaller pore-sized filter. That gives us a good overview of the surface water treatment process. We're going to focus now on groundwater wells. Most Native American tribes and many Alaskan Native villages get their drinking water from groundwater wells. And we're going to focus a little bit on how this water moves through the underground aquifers from which these wells withdraw water, and then talk a little bit about the components of a well, its pump, and the other equipment that goes into withdrawing water from the ground. We start by looking in cross-section at an aquifer system. Here we have a slide that shows a well that's been dug down into the ground, down to where groundwater exists. We show 2 areas within this photo: the zone of aeration, or the unsaturated zone, which is closer to the land surface, and the zone of saturation, or the saturated zone, in which the groundwater lies within the aquifer itself. In the 2 circles, we can show a little bit more about how groundwater fills the pore spaces between the sediments within these subsurface materials. Above the groundwater system, there's a little bit of water, the blue areas that are trapped within the pore spaces of the sand grains within the subsurface materials. There's also air present within these areas, and as a result, this is not considered groundwater, but pore water within the subsurface sediments. In the lower circle, we see that water is completely filling those pore spaces. And in this case, this is considered groundwater. Groundwater is that water which completely fills the pore spaces or the fractures in the subsurface materials. The boundary between where there is groundwater and where there's not is known as the water table. And this is the boundary between the zone of aeration, or the unsaturated zone, and the zone of saturation, or the saturation zone. As I'll show you in a minute, the location of this water table is important. Knowing this boundary can help us determine which way groundwater is flowing, and therefore where the water is coming from that may be entering our drinking water well. The last slide showed a geologic matrix of sand and gravel, where there are pore spaces between the individual sand or gravel grains, and that's where the water is collected. As we look at the geology around the country, this is not the only type of system that we see. There is a wide variety of unconsolidated materials, such as sand and gravel, or silts or clays, in which water can lie. There's also a wide variety of bedrock systems, in which groundwater is collected within the fractures, or the channels within the bedrock, as shown on this slide here. The upper left graphic shows groundwater being collected, as was on the last slide, between the pore spaces of an unconsolidated sand and gravel or sedimentary system. Next to that is groundwater collected in the solution channels or caverns that can be found in limestone or dolomite. This is often seen in the southeastern parts of the United States, such as down in Florida, where there are a number of limestone aquifers that are used for drinking water supplies. And then the lower two graphics show fractures within different types of bedrock systems, such as a basalt or other types of igneous rocks, where the water flow is only through these fractures, or the small cracks within the rock, and little to no water movement takes place within the massive component of the rock itself. Okay, so we know that groundwater is that water that completely fills the pore spaces or the fractures within the rock or sedimentary material below ground. And we also discussed earlier that this groundwater moves from areas of higher elevation to lower elevation. And it's important to know the direction of movement in order to know where the water is coming from that enters your drinking water well. The way we do that is with a water table map, as shown on this slide. And a water table map is very analogous to a topographic map. Many of you have probably seen a topo map that shows the slope of the land surface and shows where there are hills and where there are valleys. A water table map works the same way. In this case, we show a water table map in an area around 3 ponds, and each of the white lines is a water table contour. Just like a topographic contour, the white line indicates a location of equal elevation of the water table. In this case, we show that the elevation of the water table at the top of the slide is at 48 feet above mean sea level. At the bottom of the slide, there's a water table contour that shows the elevation in that location is 30 feet above mean sea level. So there's a drop in the water table elevation of 18 feet from the top of the slide to the bottom of the slide. These water table contours are developed by installing monitoring wells and measuring the elevation of the water table at a number of points in this area. And with those measurements, you can infer the elevation of the water table in other areas shown on the slide. Groundwater flows from areas of higher elevation to areas of lower elevation, and it flows at right angles or perpendicular to these water table contours, as shown on the arrows on the slide. So that if you put a well that was located just to the top of Coonamessett Pond, you would know that the water coming into that well when you pump it is coming from the upper part of the slide, or the top of the slide, flowing at a right angle to those water table contours. This information is very helpful to do source water protection planning, an issue that we'll discuss in a few minutes. Now we will look at the components of a groundwater well and describe the various features that are a part of this well system. The well is drilled down below ground, and a casing is used from the ground surface down to the opening where water is extracted from the ground. Below the casing is the well screen, or a perforated casing, and this is used in areas of unconsolidated sediments as opposed to bedrock, and the screen is used to filter out the finer materials in the sediments surrounding the well, such that only clean water is coming up through the well casing when it's pumped. In a bedrock system, a well casing is often installed from the ground surface down to a particular depth, and below that it may be an open hole where the well is drilled through hard bedrock and there's no need for a casing to keep the hole open. In this situation, there may not be the need for a well screen because the bedrock may be strong enough to hold the hole open, and you want to ensure that you have the ability to get water from as many fractures as possible to increase the yield of the water that you're pumping from the well. The size of the well screen will depend on the size of the sediments or material in the area around the well. You want to size this to optimize the amount of water that can come in while minimizing the sediment and particles that may be sucked in with the water as well. Around the well screen there will be a gravel pack that helps support the well screen and helps to provide a filter between the surrounding sediments and the screen itself. Above the screen, the hole in which the casing has been installed is filled with a grout that acts as a seal and prevents surface water from the ground surface from migrating down along the outside of the casing and entering the screen below ground. This serves as an excellent way of minimizing the flow of contaminants that may be present at the ground surface down along the well casing and into the drinking water supply. At the top of the well, there's typically a concrete pad installed around the well that is above the surrounding land surface. Again, this minimizes the impacts of stormwater. Having a concrete pad or seal at the ground surface that's above ground level prevents water from soaking down into the ground around the casing. There's typically a vent that's installed at the well that allows air exchange between the well and the atmosphere surrounding it. If the well has a pump that's sitting on the top, this concrete pad is built strong enough to support the weight of that pump. Here we show the components of a well pumping facility. You can see the well casing with its grout seal at the bottom of the slide, and what we're focusing on here is the equipment and materials that are used at the top of the well to extract water from the well and send it out to the distribution system. You can see the pipe on the right side of the slide where the water is coming from the well pump and heading out into the distribution system. In this situation, we have a pump where the impellers or the collection system of the pump are down deep in the well, and the motor that runs these impellers is placed at the ground surface on top of the well casing itself. This is fairly standard for larger water supplies. For smaller water systems, a fully submersible pump is used, where both the motor and the impellers are dropped down into the well and used to extract water from below ground. In this situation, you have the pump sitting on its pump pedestal. You have a casing running down within the well, and this casing collects the water from the impellers that are located below the water table, and the water is collected and forced up through that pipe, past the motor, and out to the distribution system. You can see the screened and inverted well casing vent. This is similar to the well casing vent we showed on the last slide. That vent needs to be there to equalize air pressure in the well. That vent needs to be screened so nothing can get into the well through the vent itself. You want to avoid the potential for insects or small animals to climb up into that pipe and fall down into the well. And the vent itself needs to be above the ground surface, at least 12 inches above the floor or the grade of the well, such that no water that may be spilled or run across the ground surface near the well can enter the casing directly. There's typically an air release valve, which is after the motor. It's shown here on the right side of the motor on the slide. When the well goes into operation, water is pushed up through the inner casing into the distribution system. There will be some air that's trapped in this line as the motor starts and water starts to move, and the air release valve removes that air so it can't get into the distribution system. And it's important not to have air within the distribution system, as it can create a problem known as water hammer, which can affect the pipes and potentially harm joints or other components of the distribution system. There also needs to be a check valve just past the motor, as shown on this slide, such that when the motor itself turns off, there's no way for water to flow from the distribution system back down into the well. You want to maintain pressure within the distribution system, and the check valve helps to do that by only allowing water to flow in one direction, from the well up to the distribution system. That gives you a good overview of the components of a well pumping facility. In terms of operation and maintenance, there's not a lot of work that needs to be done on these different components of the system. The extent of operation and maintenance that's needed for the well pump will depend on the type of pump you're using, whether it's one with the motor at the surface or it's a fully submersible pump. The propellers on these systems need to be maintained on an occasional basis, and the motor and the moving parts within the motor need to be maintained and oiled as necessary. And the engine components in the motor need to be maintained per the manufacturer's instructions. Sometimes for motors that are placed at the top of the well, there is maintenance of the bearings that help run the motor and turn the impellers, and you don't want to maintain these bearings with an oil that could contaminate the drinking water supply. If they do need to be oiled, it's typically done with a food-grade mineral oil, or the system is set up where these bearings are sealed and the maintenance of them becomes more simple and is typically done per the manufacturer's instructions. Maintenance of the check valve and the air release valve is needed on an occasional basis as well, and often that is done by a manufacturer's representative or someone that's specially trained to maintain that equipment. So let's review what we've covered to date. We've discussed the different types of public water supply systems and the definitions that come from the Safe Drinking Water Act. We've looked at how water moves through the environment and how we collect that water through a surface water intake or a groundwater well. We've talked about the different treatment processes for surface water systems and the different components of a well pumping system. And now at this point, we're going to shift gears and talk about source water assessment. The idea here is conducting a source water assessment allows us to look at the land areas and the different types of land uses in the vicinity of where we withdraw our water, either from a surface water intake for a well, understand where that land area is, and from that we can figure out what potential pollutants are being discharged into our groundwater system or into our watershed that may affect the quality of water that we're drinking. We can inventory these potential sources of contamination and put in place procedures that protect our drinking water from this contamination. The concept here is it's extremely cost-effective to minimize contaminants getting into the system in comparison to trying to treat them once they've entered our drinking water supply. And we'll show you in the next few slides how this source water assessment process works. We begin this process looking at the areas that contribute water to our drinking water supply, starting with a surface water intake. In this case, we show the intake at the bottom of the slide, and we've mapped a surface watershed showing where overland runoff of water that falls on the ground surface from precipitation will eventually make its way down to the water intake. In this case, we show a stream system with two tributaries coming together in the middle of the slide, creating the river from which the water is taken at the intake. We show the topographic contours, or the elevation of the land surface around these streams, and we've mapped an area known as a watershed, showing where rain falling on the ground surface will move towards the stream as opposed to away from the stream. If we know that surface watershed to our intake, we can look at land uses within that area that may affect the quality of water that we're drinking. If there's large livestock facilities within this area, you may be looking at manure runoff through the watershed coming into the drinking water supply and the nutrients and the pathogens that may be within that runoff. If there are significant road networks and you're in an area where road salts are applied to minimize snow and ice impacts in the winter months, we may be having sodium and chloride coming down into the drinking water supply. If there's a road network as well, you may have pathogens and hydrocarbons and heavy metals from the use of those roads that could be affecting drinking water quality as well. If the source water protection area for a surface water intake is the surface watershed to that intake, source water protection area for a groundwater well will be known as a wellhead protection area. And this is mapped by looking at the direction of groundwater flow in the vicinity of the well, as we discussed earlier, and also looking at how that groundwater flow direction is impacted by the pumping of the well. When you pump a well, you draw down the water table in the immediate vicinity of the well and create a cone of depression around the well. This is also known as the zone of influence, as shown on the slide, both in cross-section at the top of the slide and in plan view at the bottom of the slide. This zone of influence is then superimposed over the naturally occurring water table. In this case, the water table is sloping with the high point on the right side of the slide and the low point on the left side of the slide. When we superimpose this zone of influence or cone of depression, we can see the area that's contributing water to the well, which is shown as the zone of contribution on the slide, that extends from slightly below the well up to where the groundwater divide exists at the right side of the slide. This zone of contribution is the wellhead protection area, or that area where rain is falling on the ground surface, will recharge down into the aquifer and eventually flow to the drinking water well when it's pumping. Here we show a wellhead protection area, or a zone of contribution to a public supply well, in a three-dimensional cutout. We see the area where water is flowing to the well below ground, and the outer boundary of that zone of contribution, or wellhead protection area, is superimposed on the land surface. And it's that line, or that map at the land surface, which can be very helpful for understanding where contaminants may exist that could be sinking down into the ground and affecting the quality of our drinking water. Here we show the use of a groundwater flow model, a computer model that's been used to map this zone of contribution. And in effect, the computer is simulating the effects of the pumping of the well and how that changes the natural water table within this area. We see the pumping well, or the water supply well, in the center of the map, and each of the small dashes on the map represent a groundwater flow arrow. The larger the arrow, the faster the water is flowing, and the arrow shows the direction in which the water is flowing. This is created by the computer model and can be superimposed on the land area to map the boundaries of the wellhead protection area, or the zone of contribution. And you can see that boundary with the solid line in an ellipse around the well. We can take this zone of contribution, or wellhead protection area boundary, from the computer and superimpose it on the land surface, as is shown on this slide. And this can then be used to evaluate where potential contamination sources may exist and allow us to figure out how we may minimize or remove the threat of those contamination sources in order to protect the drinking water supply. How do we protect our drinking water supply once we know the location of the source water protection area? We can do this through a series of regulatory controls or land use management practices that require landowners or property owners to do certain things. We can also institute some voluntary or non-regulatory controls that will help protect drinking water. We'll start by talking about these regulatory options. And the one main control I'd like to discuss here today are the options for zoning controls through a land use overlay district. On this slide, we show in cross-section the zone of contribution to a drinking water well. We then overlay the zoning map, or the land use map, for the community on top of that zone of contribution that shows areas where industrial development is allowed as opposed to where residential development is allowed. Most communities across the country have adopted a zoning map that dictates where different types of land uses are allowed to be built. And this is true for many tribal communities as well, where different areas have been set aside for industrial use, for residential use, or commercial use. So we have that zoning map, and we can see the area where the zone of contribution, or the wellhead protection area, bisects the industrial zone and the residential zone. We can then adopt a wellhead protection or source water protection overlay district on top of this zoning map, where we can have specific controls to protect water quality for activities that may either be industrial activities or residential activities. What types of controls can we implement? We can have a series of prohibitions saying that land uses within this area cannot be built that may impact the quality of water that's being pumped by our drinking water supply. We can say that there can be no wastewater treatment plants within the wellhead protection area, or no industrial discharges of chemicals, or underground storage tanks associated with gas stations or home heating oil distributors. We want to remove contaminants that have the potential to impact our drinking water supply. So things like hydrocarbons, fuels, gasoline, cleaning solvents, large wastewater treatment plants are all different types of land uses that we may want to prohibit within our wellhead protection area. And if it's not feasible to prohibit them, we want them to be built in a way where the risk of contamination is minimized to the maximum extent possible. Non-regulatory controls or options involve a series of voluntary activities that a tribe or a community could undertake in order to protect their drinking water supply. One of the best ways to ensure that the water remains clean is to fully control or own the land area within the wellhead protection area. If you can prohibit development within this area, you can ensure that the water stays clean for a long time to come. The land can be purchased if it's not controlled by the tribe already, or an easement or conservation restriction can be placed on all or a portion of the source water protection area to help minimize potential for future land uses that may contaminate the drinking water. And the other part of wellhead protection is education, making people understand that there's an area around their well or around their surface water intake where the activities that we can conduct as a community may impact the quality of water that we're drinking. So public education on the location of this wellhead protection area throughout the tribe or the community can be very important, and regular inspections of the land uses and the activities taking place within this area can help identify problems before they become significant. Finally, I'd like to cover the last topic in this presentation, which looks at water contamination and the different types of issues that can impact the quality of the water that we're withdrawing from a surface water system or a groundwater system, both from naturally occurring contaminants and those created by human activities, and evaluate how they affect our treatment and water system management overall. This discussion will help set the foundation for other presentations within this series of discussions, including one on water system distribution and corrosion control and disinfection, as well as water storage and the different types of water storage tanks used across the country. As I mentioned, the contaminants that we'll be discussing could be naturally occurring or created by human activities, and they fall into three categories: physical contaminants, chemical, and biological contaminants. We'll start looking at the physical contaminants, and in this situation we look at turbidity as well as temperature. Turbidity is a measurement of the extent of suspended particles that are present in the water system. Typically, turbidity is measured for surface water systems and is part of the filtration and treatment process. If a surface water system is filtered, the turbidity levels need to be measured once every 15 minutes in order to ensure that the removal of the suspended particles is taking place as it needs to be. This is important because the suspended particles tend to shelter pathogens such as bacteria or viruses, which like to stick to the suspended sediments within the water column. If we can remove the suspended particles, we're removing a significant portion of the pathogens that may exist in the surface water, which is important as it minimizes the level of disinfection needed prior to the water entering the distribution system. The temperature of the water will affect the chemical processes that take place, especially for surface water systems, where we're looking to coagulate the suspended particles and flocculate them into larger clumps, which can then fall out of the water column through a sedimentation process. The colder the water, the slower this process is to take place. Next, let's look at the chemical factors for surface water and groundwater contamination. We'll start with pH. pH is the level of hydrogen ion concentration in water, and the lower the pH, the more acidic the water is. It is important to know the level of acid within the water, as this will control the level of corrosion that can take place within the distribution system piping, the storage tanks on the system, and individual homes, the copper piping and the solder that's used to hold the pipes together. The level of corrosion that takes place within these facilities is directly related to the level of the pH within the drinking water. pH also is a factor in the water treatment processes, and the type of coagulants used and the type of disinfection that's used will all be dependent on the pH of the water. pH is measured on a scale from 0 to 14, and 7 is considered neutral, or the boundary between acidic water and basic water. The lower the number, the lower the pH, the more acidic the water is. In many areas of the country, the pH of the water may be between 5 and 6. This can create corrosion within the distribution system and corrosion control practices are used to raise that pH to a more neutral level, typically between 6.5 and 7.5. Water hardness can be a factor in the water treatment process, both for groundwater and surface water systems. Hardness is a measurement of the concentration of calcium and magnesium ions in the water. In areas where water is withdrawn from limestone, you may have a harder water because you'll have higher levels of calcium and magnesium. The presence of these ions inhibits the lathering of soap such that detergents don't work as effectively within the water. And it can also build up a scale in hot water piping and hot water heaters, such that a water softener is typically needed to remove the calcium and magnesium before the water is used. The alkalinity of a water is a measurement of its ability to resist changes or buffer the pH of the water. And this can affect how water responds to chlorine disinfection and the level of corrosiveness within the plumbing systems of the distribution systems in individual homes. Alkalinity of the drinking water is measured on a regular basis, especially in surface water treatment systems, to understand whether changes to the disinfection or corrosion control processes are needed to adjust based on the level or the change in alkalinity of the water. Iron and manganese, if present in water, can cause a bad odor and taste, and it can also facilitate the growth of iron bacteria within the distribution pipes of a water system. Iron and manganese is typically a problem in groundwater systems and is found in that situation more than with surface water treatment systems, and there needs to be a filtration and chemical process put in place to remove the iron and manganese. Typically, a green sand filter is used to both filter out the iron and magnesium particles and also chemically attract them to the green sand and remove them from the water column. Sodium poses a health risk for people with high blood pressure. Sodium can be naturally occurring within the environment, but is typically a result of road salting practices in winter months in areas where snow and ice needs to be treated on the road surface. And also, radionuclides and arsenic are natural elements that are found in some rock formations which can cause cancer and other health problems. Typically, a reverse osmosis or a membrane treatment process is needed to remove these radionuclides or arsenic from the drinking water system. We've just discussed a variety of inorganic compounds, including iron and manganese and sodium. Organic substances such as petroleum-based fuels or dry cleaning solvents and chemicals can have significant impacts on drinking water supplies. The drinking water standards for these chemicals are typically quite low, and it takes only a small spill to create a significant impact to a drinking water supply, especially a groundwater system. For instance, with petroleum-based fuels, one component is benzene. The drinking water standard for benzene is 5 parts per billion, or roughly 7 drops of benzene from an eyedropper into an Olympic-sized swimming pool. That's enough of the compound to make the water undrinkable, or to have it exceed its drinking water standard. It doesn't take much of a spill or a release from an underground storage tank or a spill to a catch basin along the side of the road where it can soak into the ground to have an impact on a drinking water well. Another concern can be nitrates, which can come from agricultural operations, both from manure as well as from agricultural fertilizers applied to farm fields, as well as fertilizers applied to residential lawns. Nitrate is also a main component of human wastewater, and discharges from either wastewater treatment plants that can infiltrate down into the ground, or from individual home septic systems can impact the quality of water and raise nitrogen levels above the drinking water standard. And finally, from a chemical standpoint, lead and copper are of concern to drinking water systems. It's uncommon that you will find lead and copper in the source of water entering a distribution system, but the copper is present in the plumbing pipes within individual homes and businesses, and lead historically has been present within the solder, or the metal that's used to connect individual copper pipes within the plumbing system of a home or business. There are significant health risks, especially to children, from both lead and copper, with lead being the primary concern here, as it can create learning disabilities if too much is ingested at a young age. One of the main reasons that we manage the pH of a drinking water system through our corrosion control practices is to minimize the release of lead and copper from the plumbing system within individual homes and businesses. If we can keep the pH at a neutral level at about 7, we will minimize the amount of lead or copper that will be leached out of the pipes. If the water is too acidic, it will actually remove copper and lead from the plumbing system within the home, and this can often be seen by the bluish-green tint that will collect along a sink or a bathtub if the copper is being leached out of the pipes. Biological contaminants are also a primary concern for drinking water systems, and the main reason that disinfection is provided for drinking water as it enters the distribution system. There are a variety of different biological contaminants, including bacteria, algae, viruses, and other parasites for which we have to evaluate treatment techniques. Bacteria are probably one of the primary concerns and one of the main reasons that disinfection is conducted. They're capable of creating waterborne diseases such as cholera, Legionnaire's disease, and gastrointestinal illnesses such as E. coli poisoning. Typically, a water system will measure the level of bacteria by testing for the total coliform bacteria. Total coliform bacteria is a measurement of the overall number of bacteria that may be present within a drinking water system, both those that are harmful and create disease and those that have no impact on us. If we measure for total coliform bacteria and don't find any, we're fairly sure that none of the parasites or the waterborne disease-causing bacteria are present as well. For surface water systems, algae may be present within a reservoir or a lake or a river or stream, and the extent of algae and the type of algae can impact the taste and odor of the water, and there are some types of algae that can actually create disease in humans as well. So many surface water systems will evaluate the presence or absence of algae in its source water and develop treatment techniques to minimize the extent of algae that will enter the distribution system. Now with viruses, there are a number of waterborne diseases that are caused by virus, including the Norwalk virus and hepatitis. Viruses are smaller than bacteria and are basically small strands of DNA that can infect individual cells within humans and other animals and create diseases. They're treated through disinfection processes as well as partially through the filtration process within a water system, but it's important to ensure these are removed before the water enters the distribution system. And finally, there are a number of parasitic protozoa, or small, complex, single-celled organisms, which can be human parasites. Two good examples are Giardia and Cryptosporidium. These organisms are typically somewhat resistant to disinfection processes, and filtration is required in order to remove them from the drinking water system. And many of the drinking water rules for surface water systems have been developed in order to minimize the extent of Giardia and Cryptosporidium outbreaks within public water supplies. That concludes our presentation on potable water systems. We've covered a number of different issues, including the components for groundwater and surface water systems, the definition of what is a public water supply, some of the aspects of source water protection planning, and an understanding that knowing where your water is coming from gives you an important leg up on protecting your drinking water system and minimizing the treatment that may be necessary. And finally, we've provided an overview of the typical drinking water contaminants that exist for both surface water and groundwater systems and how they may impact the planning and management and operation of your system. To learn more about potable water systems, we've provided a few links on this slide that you can look up on your own to provide additional information and background materials on this topic. We thank you for joining us during this presentation and encourage you, if you're interested, to take advantage of the other presentations that are part of this series, including the 2 additional presentations on distribution system operation and management and storage tank operation and management. Thank you.